Okay, I believe I am live now. So it is my pleasure to welcome all of you to the conference this year, the 2020 CHPC National Conference, which is of course a virtual event. I trust all of you are managing to get online and being able to join the conference platform. So we will of course not go start the program early in terms of the speakers. So we still have time to allow more people to come online. But while we are waiting for this, as I said, welcome to the conference. This is, of course, the first time ever that we are doing a virtual CHPC National Conference. It is indeed the 14th time that we are doing the conference. And due to the unprecedented pandemic situation, of course, we are doing it virtual this year. So for us as an organizing committee, this is a new experience. And I trust that we will be able to offer you a conference according to your expectations, and that you will enjoy it. I must start off by saying, of course, a big thank you to our sponsors. Like always, our sponsors have really come to the table and are supporting our event generously again this year. As diamond sponsor, we've got Intel, and platinum sponsor, we've got Microsoft, and a gold sponsor, AMD and NVIDIA, and Altair. Of course, the other platinum sponsor is Huawei. So thank you very much to all these sponsors. It is really appreciated, and without the support, we would not be able to actually offer you this virtual conference. So we really appreciate that. Maybe I can just say a few notes on the virtual hosting. You as audience, you're really encouraged to participate in this conference. There's messaging options and functionality on the platform. Please don't hesitate to send your messages. Please also ask questions. In some cases, the recordings or the talks of the presenters are pre-recorded, so you can start asking questions right from the beginning of a talk. And in some cases, the speaker will even be able to answer you even while the talk is going on. So maybe just a big welcome again to all. We appreciate that you are joining us for this year's virtual conference. Thanking our sponsors again: diamond sponsor Intel, platinum sponsor Huawei, gold sponsors AMD and NVIDIA, and silver sponsor Altair. I encourage you, please participate in the conference. Make use of the messaging service that that's available on the conference platform, and start asking questions even when speakers start talking already, because in some cases talks are pre-recorded and speakers will be able to respond even while the talk is going on. So just in terms of the program format for the conference this year, in typical physical events, we have a workshop program before and after the conference. This we have decided not to include this year. So the program is focused on its core 3 days, Monday, Tuesday, Wednesday, but the conference tracks and sessions have been kept similar to the past. So we have our keynote sessions, our parallel tracks, our HPC applications, HPC technology track, the RISA session, as well as a SADC session. And we also have our industry crossfire later today, or the vendor showdown. This will prove to be a very entertaining session. You are all most welcome to join that. And we will end off the conference on Wednesday evening with the awards function. I can also mention that we have, in order to replace the poster competition for students that we typically have, we have a micro talks program on the platform this year. It's pre-recorded talks. Anybody can go and listen to it straight away. This is a competition, and we have generous sponsors from 4 different sponsors for this competition, with good prizes for the winners in both categories of PhD and master students. The sponsors are Qfunsoft, Gaussian, Altair, and Johnson Matthey. So we are very appreciative of these sponsorships as well. Also, the student competitions, the student cluster competition and the cybersecurity competition has been also taking place this year, although all online, and it's been running for a few weeks already now. And we are looking towards the awards function on Wednesday evening to announce the winners there. So I'm grateful also to announce that the total number of registrations for the virtual event this year is above 500 already. So I trust that all will have a very enjoyable conference. And I say again, please participate in the chat forums. This allows me now to introduce our first speaker for the opening session. So I'm pleased to announce Dr. Daniel Adams from the Department of Science and Innovation. Now, Dr. Daniel Adams is the Chief Director for Basic Sciences and Infrastructure at the DSI. And in his role, he's responsible for the development of programs that support and promote the research that develops the basic sciences, and then importantly also to ensure that the availability of access to internationally comparable research and innovation infrastructure. Now, the prime example of this is, of course, NICIS, the National Integrated Cyber Infrastructure System, of which the Center for High Performance Computing, SUNREN, and DERISA is all part. And we are very pleased, Dr. Adams, for you that you've agreed to open this important conference for us. And of course, we are grateful to the DSI for the support and funding that it is providing to NICIS. So with that, I'm going to hand over to Dr. Adams for his welcoming address. Thank you very much, Dr. Adams.
Sorry, colleagues, I just want to get my thing up here. Good morning to all our local and international attendees at the 14th Center for High Performance Computing National Conference here in the year 2020. Thank you also, Dr. Werner Janssen van Rensburg, the Program Director, for the kind words of introduction. Allow me to acknowledge and extend a special word of welcome to all our keynote speakers. First of all, Dr. Andile Ngaba from Convergence Partners Investments, Dr. Lawrence Bishor, and I'm probably struggling here to pronounce the French surname here, from University of Montreal, Dr. Thomas Sterling, our long-term friend from Indiana University, Dr. Kasim Mawatundi, Safil Halim University, Dr. Matthews Tambuka from UbuntuNet. Then also a special word of welcome to all our other guests from various countries, such as the UK, USA, Russia, Germany, India, Brazil, and the SADC countries, Kenya and Ghana, etc. And also special word of welcome to our researchers around the country, our industry sponsors and users, all students taking part in competitions and the micro talks. We always welcome our students to an occasion like this. Being the 14th annual conference, CHPC conference, it is encouraging to see that this flagship event continues to grow and remains an important event for African researchers and industry to share advances in developments in HPC and its implications on the continent. It is further encouraging to see that the conference encompasses all the components of the cyber infrastructure, which is in line with the Department of Science and Innovation's goal to consolidate as well as integrate all the components such as HPC, the communications networks, data, and human resource development in order to effectively address the grand challenges such as energy, health, climate change, and even now with the current situation now, even with economic recovery, and enable to host and lead large science projects in the country. You know, which again, the sign example is the SKA Meerkat project. The National Integrated Cyber Infrastructure System, NICIS, as Werner referred to now, promotes scientific and industrial development through the provision of high-performance computing, through the Center for High-Performance Computing, the high-speed network capacity through SUNREN, and national research data infrastructure through DERISA, which is hierarchically integrated globally as well as into local systems, necessary to provide seamless access for our research and education communities within South Africa. The conference always aims to explore the contributions and expectations of the policymakers, research communities, information, communication vendors, industry, and academia throughout a series of contributed as well as invited papers, presentations, as well as discussion forums. Vendors also have the opportunity to market their latest technology through virtual exhibitions, presentations, and exposure to key decision makers in the industry. The theme of this year's conference is machine learning and its application in HPC. The selection of this theme was motivated by the growing demand of machine applications in HPC, which mainly emanates from users outside the traditional HPC fields. This enables big data analysis in various fields and has pushed actually the convergence of HPC and big data. It is a theme that talks to all components of NICIS, as it requires the transportation of data, big data and analytics, process capabilities, as well as people with the required skills. We always try to say and will say that research infrastructure, including or cyber infrastructure, form the backbone of our country's competitiveness in science and innovation. The quality and the ability to provide the needed services and data largely determine our country's capability to produce new knowledge, innovation, and understanding of what South Africa really needs to tackle the challenges that we face. And it's for this reason that infrastructures remain central to the so-called knowledge triangle of education, research, and innovation, which in turn is embedded and integrated in a broader ecosystem involving industry, universities, and society. For research infrastructure to successfully fulfill the aforementioned enabling role and function, to establish and sustainably maintaining it to serve the needs of the scientific community and other stakeholders, adequate, sustainable, and long-term funding and effective support and coordination are always necessary and required conditions. However, the sustainability of research infrastructure goes well beyond only the entire just funding. It includes the entire research infrastructure, and that needs to be considered. Issues such as scientific excellence, unlocking the innovation potential, measuring socioeconomic impact, human capital development, as well as outreach are always critical elements apart from the funding that needs to be considered as well. The challenge is that research infrastructures are costly and ultimately funded by taxpayers. Therefore, the growing strain on our public fiscus and competing priorities such as the need to have more schools, hospitals, housing, and now even dealing with the impact of COVID-19, decision makers and funders are faced with the questions, what are the benefits of supporting these investments and operations? What are the net social benefit of costly infrastructures for the public good that they can produce? Therefore, the requirements for investment in large projects should include clear articulation of translating research into meaningful impacts of people's lives. It requires action that stretch well beyond the traditionally associated with knowledge creation, such as publications. However, the DSI is well aware of the fact that translational value and return of the investment of research in most cases have a very long lead time to demonstrate this return on the investments, and hence requires ongoing and long-term funding. Investments made in the national system of innovation, including research infrastructure, since the inception of the Department of Science and in Technology 25 years ago, have enabled government to respond to the needs of the country, especially during the outbreak of the COVID-19 pandemic in very critical areas. With the outbreak of the COVID-19 pandemic, it became crucial for government to use data-driven decision-making, which largely acknowledges and also drawing on the support of the CSIR at large, and therefore required the NICIS to fulfill very critical role in this fight against the pandemic. The CMO platform, which provides the overall dashboard of the COVID-19 status in the country, was migrated to NICIS for full implementation and for data integrity, supporting the contact tracking using the data for the mobile operators, using the Lingao supercomputing clusters to support studies to enable South Africa to respond accordingly in developing a vaccine for the COVID-19. To ensure significant broadband connectivity to facilitate online teaching and learning at all the higher institutions in the country, the universities as well as the TVET colleges during the lockdown period. When the pandemic hit the country, the CHPC OpenStack Cloud initiative became the computational and data support for the National Department of Health dashboards in providing the much needed data analysis as well as decision-making processes. Based on the country's response and available capacity, Intel South Africa, through a very competitive process and as part of the Global Pandemic Response Technology Initiative, awarded the CHPC an infrastructure grant of about 10 million rand to further support South Africa's fight against the COVID-19. And this letter of announcement was sent to the President Cyril Ramaphosa's office in September of 2020, announcing this very prestigious award that was made to the CHPC. The additional computing infrastructure that will be acquired through the Intel grant will be added to the existing CHPC OpenStack Cloud computing infrastructure to provide the more needed resources that will ensure continuation of the support of the National COVID-19 dashboard. Some of the other milestones which I'd like to mention accomplished by NICIS through the past year include the National Big Data Strategy for Research, Development and Innovation, prepared by the RISA, was approved by the DSI EXCO in July of 2020, and we subsequently submitted that to the Minister for approval. The strategy or the big data strategy is to inform planners and decision makers in the research and public sectors when deliberating about the commitments and initiatives that leverage the opportunities that meet the challenges presented by big data. Significant progress has also been made in the deployment of the new Sunrand dark fiber backbone network. This backbone network, which provides multiples of 100 gigabits per second circuits between the major metros in South Africa, will address the higher education and science communities' broadband capacity needs for over the next 15 years. NICIS not only distinguished itself as the national or the tier one platform for infrastructure provision, but also significantly contribute to skills development in the country with two flagship projects, which I would like to mention, namely the very successful undergraduate student HPC cluster building competitions, and which will also be one of the activities of this conference, the National eScience Teaching and Training Platform, with the key deliverable of this program, a structured master's degree in eScience with a physical science engineering, as well as humanities and social sciences track. The South Africa CHPC student cluster team was placed second in the overall result of the International Supercomputing 2020 Conference online student cluster competition announced on the 24th of June this year. The excellent result of the team continues the track record of successful international participation of the CHPC teams from South Africa in these international competitions. Also like to announce that the first cohort of master students graduated this year from the National eScience Teaching and Training Platform. And the aim of this program is on an ongoing basis to produce or graduate about 30 master students with focus on data science, machine learning, and artificial intelligence. Post-COVID-19, most of the industries will have to review their business models to be more data-driven, and having online presence, as people will be more and more adapting to this new normal introduced by the COVID-19. This will require significant ICT infrastructure, which most SMMEs do not have. SMMEs across South Africa represent more than 98% of the businesses, employing between 50 and 60% of the country's workforce across all sectors, and are responsible for a quarter of the job growth in the private sector. Therefore, NICIS can play a major role in the economic recovery process by a greater uptake and infusion of HPC in the industry, especially the SMMEs, for improved efficiency, as well as ICT application development, prototyping, simulations, and operating in hazardous environments. Using the model of SunRain to build affordable networks that can be accessed by the small, medium enterprises. Using the tools and the algorithms of big data analytics, such as machine learning and artificial intelligence, to assist SMMEs and corporates to define new markets and products. The government, through the Department of Small Businesses, should come on board to support grants and incentives to the SMMEs or to NICIS to drive these initiatives. Then I would like to say that the framework for quantum technology research and innovation for South Africa, which is currently under development, with the NICIS as a key enabling infrastructure of this platform, identifies niche opportunities that could also kickstart a quantum technology industry in South Africa. Coming to the last part of my address here, I would like just to say that the DSI white paper on science, technology, and innovation, which was approved in 2019, continues to put the Pan-Africa agenda on its focus and also emphasize cyber infrastructure enabled technologies as key for the fourth industrial revolution. The adoption of big data efforts in the SADC ministers, or by the SADC ministers of the SKA partner countries, with emphasis on the inclusion of big data into the industrialization strategy of SADC and other economic regions, is further testimony to continue the investment in these very important efforts. However, these should also take into consideration the complementary benefits that South Africa as a country and its industries should realize in the overall ICT developments in the region at large. However, a coordinated strategy for implementation of the cyber infrastructure framework with the Digital Advantage Initiative remains a critical need to the success of these initiatives that I just mentioned. We considered globally competitive ICT and cyber infrastructure in the country is necessary to create a sustainable ecosystem, encourages our researchers and scientists to improve their research and compete globally. The provision of modern, well-funded cyber infrastructure facilities in the country enables our researchers and institutions now here to really be competitive on a global scale. And that remains the responsibility, and we see this as our responsibility, of the DSI. And therefore, we systematically pursue our commitment, but always mindful that we cannot do it alone, but always do it in consultation with all stakeholders across the country and even in the region. Ladies and gentlemen, and with this, I would like to again use the opportunity to welcome you to this very extraordinary virtual meeting of its kind, the first of its kind, and hope that it will be a very fruitful set of engagements in the conference, and you will make the contributions, your contributions will make sure that it will be a very successful conference. So I thank you for your attention. And thank you very much and very welcome to the country.
Thank you very much, Dr. Adams, for that welcoming message. We certainly appreciate it. And I want to thank you again on behalf of the CHPC for making the time this morning to come and present to us. We certainly appreciate all the support that we are getting from you and the DSI for supporting NICIS. So thank you very much.
Thank you, Ben and colleagues.
So with that, we will move on to the next speaker on the in the opening session, and this is Dr. Happy Sithole. I'm sure Dr. Sithole doesn't need any introduction, but I can just mention Dr. Sithole is, of course, the Center Manager for the South African Cyber Infrastructure System, the National Integrated Cyber Infrastructure System, NICIS, of which the CHPC is, of course, part, and he's been Center Manager since 2019. But of course, before that, Dr. Sithole has been the Director of the CHPC for more than a decade. And I thank you very much, Dr. Sithole, for presenting the welcome message on behalf of NICIS this morning. And with that, I will hand over to you. Thank you very much.
Okay. Good morning, everyone who joined us here today live from the CSIR ICC, and everyone who is participating on our virtual platform. You are all welcome. As Dr. Adams has already made us welcome in South Africa and to this 14th annual conference, my duty is to also introduce some of the work that NICIS is doing that I would like to share with you. So first of all, I would like to really thank the Department of Science and Innovation for their support, Dr. Adams and his team, and to the DG and the Minister for supporting the National Integrated Cyber Infrastructure. And I would like to also acknowledge from the panel, Dr. Andile Ngaba, who in the past it has been very challenging to get him to participate in this conference, but we know that he's the person who always supports the initiatives of cyber infrastructure with his work as the former DG of communications in the country. These are some of the initiatives that he always gives us inputs on what to do. And we are really looking forward for his presentation today because a couple of years he couldn't make it. And we are grateful that this year he is joining us. I'd also like to, due to the virtual conference, that other people are joining us from various continents, and it's not easy with all the time zones. So we're really grateful that we're getting speakers from the US, from the East, and for them, it's really a sacrifice. And hence, we even starting a little bit later to accommodate that, but we know the time that they already sacrificed to be with us on this conference. In the run-up and preparation for this conference, I would also like to thank people who have been advising also with the conference. And this year's conference, my co-chair for the conference is Dr. Peter Bram. He gave a lot of input, including also on identifying the speakers, and Dr. Thomas Sterling, who will also be giving a keynote in this conference, and Dr. Michaela Toffa. All these have been on the panel that assisted in coming up with the concept for this year's conference. And with that deliberations, we came to the conclusion that for this year, we want to focus on machine learning and artificial intelligence in high performance computing. The drive, as already has been articulated by Dr. Adams, it's more around how high performance computing now is being revolutionized to come in and get into the other streams which were already not there in high performance computing. And this largely because of implementation of tools and algorithms of machine learning, and makes high performance computing to even go into other areas, mainly around data analytics. So the theme is mainly to come into this inclusivity of high performance computing, and hence you will hear even the talks. This will not just be from your traditional high performance computing areas. I think some of the components of this conference have already started. And in the past 3 days, starting from Friday, we have already started engaging with the students who have been busy with the Student Cluster Challenge. So they already have been hard at work. So the conference has already gone on and activities are on. So today, just this opening, we know that some of the parts of the conference are already at work. So we wish the students luck. As already Dr. Adams has indicated, this is one of the flagship for this conference. I would like to just take some time, just take you through of what NICIS is doing. We are the National Integrated Cyber Infrastructure. So the first thing for us is that we want to make sure that infrastructure is there. And I can indicate that our leadership machine, which is Lengao, has continued providing HPC resources in the country for the users in this year 2020. Even during the lockdown, we have seen utilization and availability of this system. We are already in plans. As you know, that Lengao now is almost getting to its 6th year. We are in the plans now of doing the benchmarks and implementation for the next system. Dr. Adams already touched on the OpenStack cloud, which is the private cloud for our researchers. This system has been launched now in March, just before our national lockdown. And immediately after the launch of the OpenStack cloud, there was a request for the resources to assist the country during the pandemic. And this really came up for the country, and it is operational. As you can see, it has been providing the data for the National Command Council, but also for our users. And in this process, we also have, through the Intel grant, we will also be able to get additional resources. And these resources allowed us also to open this to accommodate the other SADC countries. And we will have dedicated resources that will be given to the SADC countries and parts of Africa. This comes also with some AI and machine learning tools, which will be assisting with COVID-19 studies. So the cloud will continue to be very active and providing the resources. But we're also going to be putting in a pre-production cloud. This one, it will be now to assist our users so that they can be able to finalize their testing and before they go into our production cloud. So for those who have not yet used the cloud, they will be able to develop the tools and on our pre-production cloud and be able to move on into our production cloud. We have also put in now the 8 petabyte storage for DIRISA. This, I think, one of the challenges that we have seen over the years. It's about our users needing to have their data closer to the compute. And this, we hope that it will be able to assist because we will be able to configure this so that we can have the hierarchical storage management to link it with the HPC systems. And in this way, with our good network from Sunrun, then this should be able to provide you now with more access to your data. The backbone also, we announced last year that we have upgraded the backbone. Now we have got 100 gig across the country. And the team from Sunrun has been hard at work to make sure that we finalize the metro links that links to our backbone. And this has been going very well. We also participated in the MLAT project, which helped us to unlock the 100 gig connection for South Africa to US via the SEX and MONET cables. So that is about the infrastructure. One of the things that we're also looking at is that how do we bring in new services to our users? And for this, we have also internally reconfigured our teams so that there could be some of the resources that we can be able to provide, and you will have access to the teams within NICIS. For an example, configuration of OpenStack is becoming now pervasive worldwide, and we want to assist our users with this. So we have got a cohort of team of expertise within NICIS that will be focusing on developing the OpenStack cloud and its implementation and assist our users in that. Secondly, the cybersecurity. By no doubt, we all understand how important it is to have secure system. And for this, based on our success with our CSAT services, now we include the team that brings in the HPC experience. And this team now will be focusing mainly on providing you with alerts and also with strategies on how you should be able to protect your systems and also the workloads that you are running. Again, the other part that is very important is on the software developers. So software development, mainly to make sure that we can be able to give you the assistance in developing tools on top of the NICIS, but also where there are some other needs for you to be able to require some of the tools, this team will be very helpful. The very, very, very important thing about national integrated cyber infrastructure is scaling of applications. Because what we do, we say what you do on your laptop, you should be able to scale it so that you can be able to get time to solution. And for that, performance of your applications is very important. So we have got now a team that is looking at performance enhancement. And this team here will be looking at your applications that you run on the NICIS infrastructure and help you to be able to scale this. It could be you trying to move large amount of data, you trying to run some application and you want to really parallelize into multiple processors. And these are all what the team will be providing. Lastly, on the service desk, most of the users will be engaged in Sunrun or will be engaged in CHPC or DIRISA separately. Now, this time what we're developing is an integrated team that as the user, whatever that you require from NICIS, you will be able to get a single entrance to NICIS and be able to see all the resources that you can be able to access in NICIS. We believe this integrated services will further enhance your experience in using the national cyber infrastructure system. The other part that we're also looking at is also how do we develop research that will support NICIS. And this year we have launched now the e-research program. We have got in now with 3-year funded projects, and these projects here will be assisting NICIS with developing tools and services through research. For an example, the first program here, which is looking at collaborative and automate cybersecurity threat intelligence. This program is led by Professor Joey Joseph van Vieren from Tshwane University of Technology. And the second program here, led by Professor Petricioni from UKZN. This will be looking at quantum information and computing in South Africa. And the other program led by Professor Tim Gibbon from Nelson Mandela University. This will be looking at developing high-speed optical network technologies for novel African data centers. And lastly, we have got another program that is looking at how historically disadvantaged institutions participate in NICIS. This is one of the challenges that we see. Always you just see the people who have been involved in cyber infrastructure before, but what we would really like to see is how HDIs also participate in this. So this will be a research that will be looking at collecting data and giving us that information. And we will be advertising the next call. And for this, we would like to make sure that we have got more participation from historically disadvantaged institutions. So look out for this call, because we really need you as the researchers in South Africa to contribute in the development of NICIS. I'm not going to dwell more into this part here, just to highlight these projects, because Dr. Adams has already touched on it. But all what I can just indicate is that during the lockdown, we have realized that cyber infrastructure can come through for the country. And there has been in a number of things. In predictive analysis, we have seen that we have come in terms of online learning support, mainly in looking at connectivity, how we provide the connectivity for the students, understanding where the students from higher education institutions are and what is the connectivity coverage there, and advise the country on how to provide those students with the proper tools for them to study. And in future, we will be looking at connectivity models of access to facilities for students. For an example, one of the things that we're looking at is how can we expand EduRoam so that you're not only getting EduRoam when you are at home, when you are at university, but if ever there will be possible for you, for the students also to have EduRoam when they are at home. So these are some of the things that we will be looking at to assist with the online learning in the country. Lastly, it is very important that we acknowledge our sponsors. Werner has already touched on this, but I thought I should also reflect on it, because it is through these sponsors that we are able to host this conference. And also, they're not just only coming as the sponsors, but they participate in the conference to share with us the developments in their technologies that assist on cyber infrastructure, and we are very grateful for their support. So the other sponsors again that we did indicate, and for this, NICIS is not just about the infrastructure. It is very important also to enhance the participation of our researchers and produce good quality research. And I think these sponsors, which sponsor the competition, for an example, the student research, the companies that you see there, they push our users to be able to come up with innovative solutions in using cyber infrastructure. And it is very important. And the last group of sponsors there, which are looking at the student challenges, these are the competitions that we said have already started, and it is to encourage the students, and we are very grateful for those sponsorships. I know that there will be prizes, and since we are in a virtual environment, I'm hoping that the students won't be receiving virtual prizes. There will be real prizes. But thank you for the sponsors. I will be looking forward for those award of prizes and see how we will be delivering these prizes to the students. With that, I would like to thank you, the participants, and I want to wish you very well through this conference. As you have seen, the program is really loaded with very good talks and also fora, and I'm hoping that you are going to take advantage of that to participate in these discussions, because we also like to get your feedback on how you want the national integrated cyber infrastructure configured. What are some of the services that you need? So during these 3 days, I'm hoping to pick up some of those from you as the users and the participants of this conference, because we can only grow with your assistance. I would like to thank you.
Thank you very much, Dr. Sithole, for that welcoming message. Your words are appreciated, and I think it's a very proper start to the proceedings of this conference. Thank you very much. We will now move to the next speaker in the opening session, and Dr. Sithole has already alerted to this, but we are of course very appreciative for Dr. Andile Ngaba, that he is committing his time as the first keynote speaker for the conference this year. And maybe allow me just a bit of time to give a background of Dr. Ngaba. Now, Dr. Ngaba is a South African businessman who has devoted most of his life and career to the field of technology, in particular communications. He is currently the chairman, founder, and majority shareholder of the investment group Convergence Partners. And through Convergence Partners, Dr. Ngaba is also involved in significant communications infrastructure projects across Africa. And you will, if I mention some of this now, you would immediately recognize the names. The first one is CCOM, which is the first undersea fiber optic cable system serving Africa's east coast, which was already ready for service in July 2009. He's involved in the first private sector satellite in Africa called the Intelsat New Dawn. He's also involved in a joint venture to bring high capacity long-haul terrestrial fiber to South Africa, so-called FiberCo. And more recently, a new joint venture with Google to invest in C-Squared, which is a broadband infrastructure company headquartered in Nairobi in Kenya. So you will agree that is significant projects that he's involved in. And maybe just one or two more things. Dr. Ngaba was previously an activist aligned with the ANC during the struggle against apartheid, and thereafter, as Dr. Sitore also mentioned, the Director General of Communications in the first democratically elected government of South Africa in 1994. Now, he left government in 2003 to pursue a career in the private sector. And his passion for social development and desire for innovation in the ICT sector, especially on the African continent, is evident in the work that he's doing. So I trust all of you will agree that we could not have asked for a more appropriate first keynote speaker for the 2020 CHPC National Conference. Dr. Ngaba, we are indeed pleased that you are joining us this year. We've asked, of course, previous years, but we are really pleased that you can join us this year, although it is a virtual event. So we are really looking forward to your presentation, which is entitled From Centralized Hyperscale to Edge Cloud and Edge AI. Thank you very much, Dr. Ngaba. Over to you.
Thank you very much. Much appreciated. And I just want to bring my Can you hear me?
We can hear you, Dr. Ngaba.
Okay. I just want to move this. Can you see my screen?
Yes, I can see. It looks like the home screen of your, yeah, now the slides are coming up.
Are you able to see my?
Yeah, we can see that, Dr. Ngaba. So if you can maybe just make it full screen, then it will be perfect.
Okay, thanks. How is it?
It is still not quite full screen.
Sorry. How is it now? Sorry about that. I'm using two screens here.
Okay. Yeah, that is looking good.
Thank you. Apologies for those few minutes of delay. And thank you very much, everybody, for really allowing me to be part of this event today. And I really appreciate, thanks to the program director, Bernard, thanks to all the colleagues here, Dr. Stolle, Dr. Adams, really for putting this together. And we are having this in the middle of a pandemic. So very clear that this pandemic has brought about a lot of innovation in so many ways. My talk today is more going to argue that as we build centralized hyperscale, there is a new revolution happening on the edge, which we need to think about. I'm just going to talk about 3 parts here. One, HPC overview, the architecture, and the context of South Africa. And I'm going to come up with recommendations towards the end of my talk. I think we all know and can attest that HPC really, it provides excellent computing power, and enhanced performance in running advanced applications. This is something that we all appreciate. But more importantly to me is the increase in solving problems in business process, social, and economic research. And this is what really, I think today is all about. From a benefits point of view, I think the earlier comments were that, the fact that HPC can handle high volumes of data is something that attracts a lot of us, business, academia, research, public sector in this environment. And also the flexibility to match infrastructure configuration to the applications. And the fact that we can scale up and down as and when you want. And the cost-effective nature of operations. More from an OpEx point of view, addressing issues of power, cooling, etc. Now, the areas that we see, HPC today being adopted widely, in manufacturing, in fintech, in mining or oil and gas, in retail, in healthcare, media and entertainment. These are all areas that today, no more use HPC for research, but for applications that are needed by clients. Where clients specifically find out whether, what are you running this application on? And because they are actually interested in exactly what, Sorry?
You can continue, Dr. Ngaba.
Okay. So one of the, I think for us as a country, critical is how we use this infrastructure to solve our problems. Problems of unemployment, we have a lot of young people who graduate and we don't know where they are, who they are. We need to begin to look at this technology, how we can use it to solve our, I've identified key 3 South African problems. One, inequality, issues of corruption, where this technology can be used to track almost everything that government is buying, from whom, when, and be able to understand that ecosystem. And also, as I've said, address unemployment. We need to begin to look at, such a technology as a way of solving real issues that confront us as society. I think the examples by both Dr. Adams and Dr. Stoller about the use of high-performance computing in health during COVID is a classic example of responding with such technology to social and economic needs. Now, from a point of view of architecturally, I think, as I've said earlier, the massive scale of compute, network, and storage for various industry uses, as I've explained, and HPC or high performance computing utilizes this software approach in automation. The topic today, it's all about AI and ML. And that, it consists of HPC in these days, will consist of, virtualization, software-defined networking and software-defined storage, and again, software-defined container engine. This allow easier deployment and management of applications and integration and orchestration such as Kubernetes and OpenStack. Again, this was raised earlier. Due to reduced costs, I mean, this no longer just resides in data centers, but can be now extended to edge of the network, which is really what one is talking about. I think CloudFront demonstrates this, I mean, use of OpenStack, I mean, and how both compute networking and storage, I mean, all get put together in this OpenStack shared service environment to be able to provide services today to enterprises. Now, I mean, as I was saying, HPC before was known to be used for research, not at all. Today, this is used for clients. We deploy these for customers who really want to do much more complex environments. Now, just to take a little bit of a deep dive, I mean, apart from the ability to scale, I think, I mean, technologies specifically used to differentiate HPC clusters with simple DC clusters, I mean, which we have in our data centers, is this container engine and orchestration. I mean, with most of the applications moving to Docker containers, HPC should be, you know, powered with Docker containers to ease deployment. And therefore, Kubernetes is now a very important component of HPC. And many HPC environments now provide this non-VM environment as well. I mean, which is something that we really appreciate. Now, the other very important issue is packet acceleration. I mean, I think this is very key, I mean, to accelerate the network. I mean, and what, for instance, we have seen. And then also CPU pinning and the NUMA modes. I mean, this is again, you know, something that we believe that is is one of the differentiators that we see in this environment. Flash storage and GPUs, basically, GPU support. And this, again, for processing AI and ML application becomes very, very critical. I mean, public cloud players now do enter this game. I mean, we do, for instance, see when you want to go to AWS, Azure, or GCP, now are providing the ability to pre-own, you know, HPC racks. I mean, which with the ability to spin up applications using, I mean, public cloud provider APIs and consoles. I mean, this is something that we use on a daily basis for clients. I mean, AWS has launched Outposts, I mean, and we are engaging AWS to make sure that we become leaders, number one, in deploying these. I mean, last year, this time in Vegas, I mean, that's where AWS basically launched this, and we are looking forward to see this in a number of countries in our region. Again, management of these clusters, I mean, are through this standard AWS console and provide this seamless testing ability, I mean, in public clouds and on-prem environment. So AWS, Azure is providing Azure, you know, edge stack, and GCP with Antios, which gives you an ability to have this multi-cloud environment. Now, just expanding HPC to the edge, I mean, as I've said, it's something that we, you know, is very, very important and relevant. I mean, with Kubernetes and OpenStack to play an important role in HPC, it's something that we all are very excited about. And, you know, open source components to keep costs low, again, is very, very key. I mean, you know, I mean, the open source foundation is working strongly to really advance HPC on the edge. And these, again, will be used to deploy AI, ML, and IoT and other very important applications such as driverless cars and many, you know, virtual reality and many others that will be needed. Now, one of the things that I wanted to really, you know, to talk about is the fact that, I mean, this fostering of AI and ML and HPC, you know, that these applications need for high performance compute coupled with GPU cards. HPC clusters provide necessary resources for for analytics. I mean, in video, for instance, or big data, or in training, or for inference, for instance. So with the advent of TensorFlow and TensorFlow Lite by Google, and this again is very easy for pre-built inference models to run on HPC compute. And this is something that we really see, I mean, as the TensorFlow community in the African continent. Again, NVIDIA, with its CUDA architecture and Tensor, I mean, RT acceleration has made this, I mean, again, deploying and leveraging graphic cards in HPC cluster very easy and something that can be done. So graphic card manufacturers also are providing drivers to enable virtualization on graphic cards. So what in essence I'm saying, I mean, HPC is becoming very commercial. It's something that today is becoming available for use in various segments of the market that I've talked about. I mean, this is a classic, I mean, NVIDIA HPC framework, I mean, which I suppose NICIS has already or deploying or using, whether, for instance, computational fluid dynamics, life sciences, I mean, and computational physics, and a number of areas. And this using standard languages and libraries, I mean, and all this means that, you know, with Python, with R, with a number of languages, we can be able to access this infrastructure and use it extensively. Now, I think for me, it's very important to also bring together 5G and adoption of HPC. Basically, I mean, 5G is something that we research and follow very closely. But before, I mean, I just talk about this slide a little bit in detail, is to say that, I mean, with, to Dr. Stoller, with what we have seen during COVID, I mean, one suggestion I want to put across in this keynote is that I think, you know, with what we have seen and during COVID, I mean, and the impact to universities and learning in general, we need to think about a special license for NICIS, for TENET, for Sunren, for universities to drive connectivity, because to rely honestly, you know, and saying that you will be working under the framework of the existing licenses, that is going to hold you back, not only in research, but also just in learning, in advanced learning. I mean, I think that we need to come up with a model to license universities with a special type of an ICASA-based license, and to license NICIS and Sunren not to follow the current regime of licensing, because I think COVID-19 has demonstrated that, you know, this actually will stop learning if you have a pandemic like this. So we need to think about how then do we do this. For instance, one example, I mean, there are two infrastructures we use is optic fiber and spectrum. One of the suggestions I want to put across here is, I mean, we are busy now with E-band somewhere between 60 and 90 gigahertz. When I look at what you are talking about of 100 gigabits per second connectivity between your nodes, you need to be moving to terabits per second in nodes as universities and NICIS nodes or Center for High Performance Computing nodes to be able to connect. I mean, the gigabit network is basically not going to be able to support you in what you want to do. And the private sector is still at gigabit level. Research should be at terabit per second level. Now, for you to be able to do this, you need to get your own, I mean, license framework, so to say, your own spectrum. I mean, one of the areas I suggest, I mean, to include as part of the NICIS package is above 90 gigahertz range, which is now being used and experimented. I mean, IEEE has got what is called the standard P802, I mean, .1, which is, or .15 rather, which is a standard for what is called WPEN, to allow for these high throughput connectivity. I mean, I think we can't be teaching, I mean, HPC with pipes below 100 or below 1 terabit per second between nodes. So it is for that reason that I argue strongly that, you know, the HPC or the NICIS infrastructure of connectivity or the network should move into terabits per second rather than gigabits per second. Otherwise, this, I mean, you know, whereby you run these, you know, big clusters at one level, but your network is very, very slow, it will actually, you know, cause a sort of a dysfunctional model in my view. So from a 5G point of view, I mean, I've written about private 5G networks, which I argue that universities and NICIS should run private 5G networks and have their own spectrum to be able to drive, for instance, you know, access to these clusters and nodes. Otherwise, you know, you would find it very difficult, you know, people in the Eastern Cape, people in KZN to access your infrastructure. The other area I want to talk about is open compute that, I mean, as South Africa or as NICIS and academic community, we really need to participate strongly and have chapters both in South Africa and in the region. I mean, as part of OCP or Open Compute Project, which is an alliance of vendors and enterprises and research institutions, so that we can start now to begin to build, you know, this hardware ourselves. I mean, and join the community in the world that is building this infrastructure. So it's one recommendation, really. I believe that we need to start to think in this direction. Again, I mean, modular data centers, I mean, again, this is Vapor.io as an example. I mean, with the advent of 5G and modular data centers running HPC, it's becoming a norm, specifically targeting these low latency applications such as self-driving cars, AR and VR, etc. You know, I mean, Vapor.io has built this simple plug-in and play, I mean, container data center basically, with 5G radio to seamlessly scale HPC clusters. So this is very real and these things are happening. And AWS Wavelength is another example of HPC cluster, I mean, by AWS rather partnering with Verizon. So in essence, what one is saying, modular HPC data centers enable quick scaling, I mean, and low latency that we need to consider in this. Now, in South Africa, you might have seen in the fourth industrial 4IR report that was submitted to the president, there's a chapter there dealing with infrastructure and resources. And we have covered in that report what should happen with HPC in the country. You know, we need to invest in human capital, build infrastructure, basically, I mean, create these platforms. And the report on Center for High Performance Computing is that what is being said there, in order to truly achieve, I'm quoting this verbatim from the report, to achieve digital transformation, but what government needs to leverage Center for High Performance Computing, way more than what is happening to this. So the traditional HPC workflow of modeling and simulation are transforming a new range of new state of high performance computing, including what we talk about, you know, high performance computing, AI. I mean, and create what we suggest is the creation of a grid, a national grid. I mean, and that will be supported by provincial, these edge grids or open data. So the Center for High Performance Computing is well placed in our view to serve as the government on-premise super cloud, basically, and be part and create this national grid of HPC capacity. I mean, this can be white labeled, for instance, as a multi-cloud capacity from hyperscale. In some areas, you don't have to invest in all the hardware, all of it yourself. And that government must also create these data lakes, I mean, within the Center for High Performance Computing platform to perform these AI analytics and partner with private sector to do this. I mean, these data lakes will contain data from the state, from the internet, from social media, and other environments. Now, from what we are proposing there is that the high performance computing strategy in South Africa should really take into consideration by building this world-class supercomputing, which has been done, and congratulations to the leadership of Dr. Sithole over the last 10 years. Consistently, you know, he's participated in global, competitions. They've done great. What we're critical today is how do we build a national grid and take edge into consideration to be part of this? I mean, what one is saying, the national computing grid architecture based on edge, position these data centers, exploiting the subsea cable, even the Eastern Cape now in PE, there's going to be a submarine cable node landing there by Facebook at about 180 terabits per second in that node, which in essence, it gives us an opportunity as NICIS to come up with new models of participating and creating this new architecture that I've talked about. As I've said earlier, that licensing is key. I mean, we need to design a type of license for NICIS, for universities. I mean, you cannot operate in the classic environment. I think the challenges of COVID, as I've repeated earlier, that, you know, we can't operate in that way. So the strategy will, from an availability point of view, provide the secure cloud supercomputing services for a wide range of public and private users, and then encourage innovation, and also increase accessibility, basically. I think Dr. Adams talked about how SMMEs and startups now need to exploit this infrastructure. So, I've sort of added, as I conclude, what I believe that NICIS should really also consider. If you look at the price of Bitcoin today, and the price of Bitcoin at the beginning of COVID-19, I think it shows that we need to not only think about blockchain for cryptocurrency, but for a variety of reasons and services, that if NICIS can bring blockchain as part of your arsenals, if I say, and that universities must become nodes, basically, in building, this infrastructure, basically. And all universities must be assisted to set up this. This is basically the suggestion. So that they have access and build this infrastructure and participate in becoming, nodes for hash functions, basically. The last part I want to raise, program director, is that in Europe, there's what is called CISPE, which is a trade association that gives voice to cloud infrastructure service providers in Europe. And we are in this, through the Digital Council, trying to, we just had a conference last week, mobilizing the community in the cloud hyperscale environment to come together so that when we engage you as NICIS, as government, we can have some form of a collaborative model, that we can work together. I think the European community published what is called the Digital Services Act, which I would encourage that you look at. CISPE's response to that, which really is a very good model to take forward. So from an advocacy point of view, I'm glad to see that there are members from SADC here. I think for us to be able to do this effectively, we need a lot of advocacy in this area. Even in TVET colleges, we need to begin to make sure that the startups and SMMEs, the competitions that you are doing should involve the incubators in the country. So that HPC does not become only something that sits in research and academia, but it must begin to enter, startups and SMMEs, in particular in our region, in sub-Saharan region. One of the most important issues that I suggest that also maybe NICIS can consider is the Center for Open Data. It's good enough to have this high computing power, high computing power that we talked about. But with all the laws that we have, it's still very difficult to access data on an anonymized basis in South Africa. And we need to do this and have clear guidelines on how, for instance, Center for Open Data, which could either be part of the NICIS family, in order for us, when we use HPC, data does not become a problem. And I think building Center for Open Data as part of NICIS, would really improve, or create or improve any open data that we want to access, either from public sector or private sector. Remember, taking into consideration POPIA, taking into consideration GDPR, and all the laws and regulations that govern data. So that is really what one is, putting in this as one proposal, suggestions, but just to kickstart this. Now, who is Inc? Inc is one of the companies of Convergence Partners. We are in West Africa and Southern Africa, and involved in what we call edge AI and video analytics. We use HPC in our day-to-day life and environment for retail analytics and intelligence security, and what we call compliance as a service in the mining, in particular, cobalt and diamond mining, where we actually assist mining companies with using TensorFlow for analytics of video and being able to manage the infrastructure that they've invested in. So that is really what my short presentation is all about. Thank you very much again, colleagues, for giving me this opportunity to talk to you this morning. I sincerely appreciate your time.
Thank you very much, Dr. Ngaba. As indicated in the beginning, we really appreciate you making the time and bringing this interesting presentation to us. I think myself and the audience will agree that the points that you touch on is certainly well aligned with the focus of our work, and your insight is certainly appreciated. So I've seen one or two questions here. I've not read all of them, but I see we do have a minute or two, Dr. Ngaba. Are you okay if I maybe read a question or two to you? Yes. to respond? Is that okay?
Yes.
Let me see. I've not prepared my...
No, I can read them. Don't worry. I can see them.
Oh, you can also see them.
Yeah.
I'll take one there about the Center for Open Data. Having a Center for Open Data at NICIS is a great idea. I'm sure NICIS works with a wide range of partners, private, public, academic, and so on. So it seems to be more like a comment, but yeah, that's drawing some attention.
Just maybe to I think we really, the suggestion is coming out of, I'm sure we saw what happened during COVID. Dr. Stolle and his team, they were looking for data from multiple sources to be able to do analytics. They had the computing power. You need social data, you need a lot of issues, but we all understand that unless you have this open data policy, open data laws, where anonymizing of data is done and to the satisfaction of regulators like POPIA, like all the people who deal with regulations, it's something that needs to be done. I think unless there is, as part of the NICIS family, that this open data, Center for Open Data, where there is a continuous gathering of data for purposes of research, that will complement your HPC infrastructure, rather than purely just deal on the compute side. In particular, if you look at the topic today, it's about AI and ML. AI and ML, you need volumes of data, and that is why really I'm saying that's what really is important. But lastly, my comment about what I said, that with the challenges we have seen, universities and kids unable to get connectivity. You cannot solve this by becoming a buyer as NICIS, as Sunren, as Tenet, as as universities. We need, as yourselves and us, to begin to debate about what type of licenses are really required for universities, so that universities must get the spectrum, so that universities must be able to work, freely, without having to pay the price of data that we are paying today, for research purposes a student at Nelson Mandela University that has to go to Transkei, a master's student or a PhD student, for him or her, how much is she going to pay to be able to get connectivity? So this is very important. I think the COVID-19 period has given us an opportunity to rethink, while we have Tenet, while we have Sandren, while we have NICIS, to say, what do we do, in order to enhance connectivity? We should be talking about, a minimum of 100 terabits per second per node of connectivity in that national grid that I was talking about. So these are some of the issues. I'm sure when we get time, we can further, take a deep dive and discuss them. But those are my recommendations to you, colleagues. And to
most certainly, you are talking to many aspects that are close to the heart of NICIS and what the CHPC and Sandren and the RISA is endeavoring to do. So, yeah, no, most certainly. Thank you very much for those insights and comments. I do not see any more questions. Let me just have a look quickly. Maybe a last one, Dr. Ngaba. This is a question from Quinn Reynolds. I've not read it, so I'm reading it now. Thank you for an excellent presentation. Just a comment, a Center for Open Data is an excellent idea, especially for results and outputs from publicly funded research. This can help accelerate adoption of traditional HPC functions, such as modeling and simulation, as well as modern data-driven applications. Yeah, so it's more like a comment from Quinn. So thank you, Quinn, for that comment.
Thanks a lot. All the best, colleagues. We'll be joining the rest of the sessions in the course of the day, tomorrow and the day after.
Thank you very much, Dr. Ngaba. So this then brings us to the close of the opening session of the 2020 conference. So maybe just allow me one or two final remarks. You will all by this time probably have seen the program and the timetable. So please make sure to log in at the appropriate times for the following sessions. The next session that will go live is Keynote 2, that is going to be delivered by the conference diamond sponsor, that is Intel, by Mr. Stefan Gilic. So please log in for that. That will start at 12:15, so it's 12:15. And then later on at 2 o'clock, we will have the start of the first parallel track sessions, which is 2 sessions. It's the HPC applications and the HPC technology tracks, which we do have very interesting talks in those 2 parallel tracks, and that will start at 2 o'clock. So with that, thanks to all that joined the opening session of the conference, and we're looking forward to your continued participation in the rest of the event. So thank you very much, and talk to you again later.
Dora, you can go ahead.
Okay, thank you. Good day, ladies and gentlemen. I'll be chairing this session today, and it is a privilege for me to be sharing this important session. So before I can talk about the speaker, I want to introduce myself. My name is Dora Tobie. I'm the technical manager for the NICIS Center for High Performance Computing. And maybe before we can, for the people who are just joining, maybe the house rules, there is a question and answer button or box at the bottom. If there are any questions during when the speaker is busy, you can post your questions there. There is also a chat box where general messages can be posted. After the speaker has completed, we will then attend to question and answer. Our speaker today is Mr. Stefan Gillick. He'll be speaking about accelerate insights with AI and HPC combined. So I just want to take a moment and read up Mr. Gillick's bio. Stefan Gillick is the Director of Artificial Intelligence, GTM, in Intel Data Center Sales. His responsibilities include the positioning of Intel solutions in the artificial intelligence environment with a focus on AI accelerator technologies. Together with his cross-site and inter-organizational team, Stefan plans and implements strategic worldwide. Stefan joined Intel as a computer scientist in the supercomputing division. Since then, he has gained comprehensive expertise from edge to cloud in numerous business areas, and he has held various management positions with responsibility for technology and the positioning and marketing of relevant products for business, industries, and end users. As a member of the steering committee of the Digital Video Broadcasting Project, Stefan has also worked towards the expansion of unified standards in the media industry. Stefan holds a degree in computer science from the Technical University Munich. Stefan, I welcome you into the stage. You can start with your talk. Thank you.
Yeah, thanks a lot for that kind introduction. So I will start to share my slides with you, and I hope you will all be able to see them correctly. If that's not the case, just let me know, right? Okay, so today we came together to talk a little bit about AI and HPC and how we combine that best. A few words were said on my role already. Just the one thing I wanted to remember, some people here might know me from my previous roles, which were in high performance computing, and I changed my focus into AI about 4 years back. And by the way, AI was always one of my, if you want to call it, hobbies, because at university more than 25 years ago as a student, I came in touch with AI, and I always found it fascinating. So I've been following it through the AI winter, as we call it. And now we see obviously the blossom of AI again. And that is why I got back into that area. Okay, today we're going to talk about technology and some forward-looking technology, also performance details and other things. So please note this disclaimer here. Some of those things can change as they are forward-looking, right? So today we are here virtually, right? When my colleague asked me whether I could do this keynote here today, and it's an honor to be here with you today virtually, I remembered one of the most impressive times I've been at CHPC. I've always been following or being there from time to time, not the last 3 or 4 years, but in 2014, I remember very well being here physically. The CHPC was back then at the Kruger National Park. And I liked that a lot. That was, I think, the most exotic conference location I ever been to. Hopefully, we'll be able to meet again soon. We all know the circumstances, and if that would be in that location again, it would be really great. So that's one difference, 2014 to 2020. The other one is more on the technical side. When I remember back at that conference, very few were talking about AI, right? It was mainly about modeling simulation, though the core of what we call HPC. Now times have changed, and we are talking about HPC and AI combined. And that is definitely what I want to talk about to you today. So let's see, I have divided up my talk into three parts. First of all, let's look into where AI and HPC actually overlap, where they converge, and what kind of principal imperatives we can deduct from that. Then I want to look briefly at what I call the journey. It's about how do you actually bring AI solutions together. I think it's worthwhile spending a minute on that in principle. And then after that short excursion, we'll look into how do we fill this with life, right? How does the solution look like? Which kind of hardware, software stacks, which kind of ecosystem do we need to bring things forward? So that's the structure of my talk today. So, insight was the subtitle of my talk, right? And what is important today more than ever before is the time to insight, right? It's very critical if we think about the reason why we can't be together in one room today, the COVID crisis. We see how important time to insight is. If you want to know more about how the virus spreads and how we can actually fight it, that needs to happen very fast. Drugs need to be done very fast, and they actually have been done very fast with the help of HPC and AI. So we see the best example of that already today, right? But there's other examples. How do we find cleaner energy, right? It's up and foremost problem that we have to solve very soon as well, and work more on it. How do we actually get better weather forecasts so that we can avoid weather phenomena, catastrophes, and other things, right? So there's many examples also out of automotive and other industrial areas where HPC and AI is actually being used, and we need to find those solutions, obviously, in a limited time, which the COVID example shows very clearly. So how do we do that, right? How do we actually use AI and HPC combined so that we actually minimize time to insight and make insight actually possible and very qualitatively as well? So let's look into AI and HPC a little bit, right, from its principal point of view, and see what they have to do with each other, right? Everybody is speaking about this convergence, but I've seen that there's obviously many opinions out there on where it converges, where it overlaps, and how we can use this to our example. So if you look like what AI does, right, specifically deep learning as a subform of AI, machine learning, and deep learning, what we get there is knowledge, and knowledge is discovered out of data, right? So out of images, large amount of images, speech, we do natural language processing. And how do we do that, right? We use either classical machine learning. So in general, algorithms which have the capability to learn on data, or we do that with so-called deep learning with neural networks. And there's other methods as well, and there's constant research on that as well, right? If you look at HPC, what we do there is simulation. We model the world and simulate the world, and then we make predictions. So that is used in climate and weather prediction, genome sequencing, seismic analysis, in finance and fraud detection, and many other applications which we know since a long while. How is that done? Well, we do it with a numerical analysis. So we need a lot of compute cycles for that. We need parallelism, massive memory, and a high throughput. Okay, So if we look at a possible combination, right, I found actually two which are very interesting. One is I want to call AI on HPC, right? That's very simple and straightforward, because if we say we can use HPC methods in terms of having machines which have a high performance, can we use that for AI as well, where I need a lot of performance as well? The answer is yes, right? Even if the calculations can be different in terms of the data types being used, we know for numerical simulation, we need to have very high precision usually to make the algorithms converge. For AI, that's a little bit different sometimes, right? You can reduce the data types, but essentially you need high compute power on both ends. So that's AI on HPC. On the other hand, what I can do is to achieve what I want to achieve in HPC, to predict how the world is behaving in several aspects, for instance, climate and fraud detection and other things, right? I could use potentially AI as well, right? The methods of AI, looking at data, right, and then analyzing that data, I can also use to do things which I used to do and still maybe do in HPC, but combine it in a way that I use this method as well. This is what I want to call HPC and AI, or HPC on AI. So it's a very simple principle. Obviously, you can have different opinions on that, but I offer my opinion here, at least for the overlap of HPC and AI. Now, let's look into how that looks like from a principle point of view, right? In some applications in the real world. So what we can see here is that we have different ways how HPC on AI is actually working, right? So I can have AI integrated into HPC workloads, which means that the workflow basically uses simulation as well as AI-driven data analytics, and uses that for the benefit of the application, right? The other one is AI is just simply accelerating HPC simulations by, for instance, selecting the right simulations to do and avoiding simulations which will not converge or not deliver usable results. And what I also can do is replace some of the HPC simulations with AI methods. So these are three different ways how HPC can work on AI and with AI, right? And in a practical example, you see here on the right side of the slide, what does that mean for drug discovery, right? So I can, for instance, determine the next series of molecular dynamic simulations, right? So select the right ones to do. Or predict response of drug properties on tumors, right? Based on data I have from experiments. So basically mixing the real world where I have data on experiments with the predictions I get from simulations of the molecular dynamics of this drug, right? And very simply, I can also use AI encoding reports for analysis, and AI is always good when it comes to a lot of data and making the best analysis out of that. So I can use it that way as well. So there are a number of things where AI and HPC can work together very well. Some people would call that convergence. And I call it, in this case, HPC on AI. One other very concrete example from the CERN Open Lab is to use AI basically to approach one very basic thing they need to do and see whether you can do it more effective. Now, I have been working with the colleagues at CERN Open Lab for a long, long time, a very fascinating thing. Maybe some of you in the audience as well. What they do is basically very complex physical and geometry modeling. And for that, Monte Carlo simulation is being used as a central element. I won't go into details here. Obviously, that's very interesting, but I can spend the next 2 hours talking on that. I won't do that. The thing to remember here is a lot of the cycles go into that, and that's going to increase in the future as they increase the energy where they actually collide parts. On the right side, you can see a few photos of that, of the experiment itself, right? The Large Hadron Collider, which is near Geneva, 100 meters below the ground, where they accelerate the particles, and then they are collided, and you can see on the top a nice symbolic picture of that. So what they want to do there is basically to trace the particles, right, and by that way find out whether the reality matches the theory, like they have done before, right? So that is what they do, right? And Monte Carlo simulation is a very central element for that. Now, there was an idea to say, okay, can we do something with AI, with an AI method, in this case, generative adversarial networks, so-called GANs, to replace some of the Monte Carlo simulation necessary? And yes, they can do that. And they need fast training basically to build these complex models and generalize them to different detector geometries for the particles. And you also want to have fast inference, which is the usage step of deep learning, to allow the data generation on the fly, and that way not save everything, but just save the events which are actually nice for your analysis, or fitting for your analysis. I want to say thanks to Sofia Vallecorsa at an Open Lab for allowing me to share that, because I like this use case very much, right? It shows very clearly where AI and HPC can come together for the benefit of this type of simulation. Okay, so I hope you have seen where AI and HPC have something to do with each other, and how they can help each other to achieve the results we want to achieve, which we have been doing with HPC before, we can now do with AI and HPC combined. Now, let's look a little bit in the AI direction, right, and discuss a few principal things of AI solutions before we come into more technical details. All the AI solutions I've seen so far are going through 4 principal steps. And it is essential to understand those steps to know where you have to actually put your emphasis on and how you actually work an AI solution. So there's 4 steps. One is the discovery step. The next one is a data step. Third one, development step, and the deployment step. In the discovery step, you basically look at the possibilities, what you actually want to do, right? What are the things you want to achieve? What is the data you have? And then how do you approach the problem? It's also in this phase where you, in the case your data is confidential or it's protected by laws, you need to resolve that at this stage. Then there comes the data step, which is the technical step around data, which is very, very important to basically see where you store the data, how you prepare the data for the AI modeling, for the training, and clean it up, right? This is very central, right? And in a concrete case where we were looking at, the customer was looking at pictures of a large industrial structure and trying to find out from these pictures or drone videos where the structure has actually corrosion and where some maintenance work needs to be done. In this case, this data step, right? Looking where the data comes from, where do you store it, how do you clean it up for modeling and so on, was actually taking 12 weeks in the POC we did at that time. And that was actually substantial time just invested into the data phase, which has nothing to do with AI yet, but just the preparatory status. Then the develop step number 3, is actually the most interesting ones for us in AI. This is where you select the models. This is where you train the models in the case of deep learning. And that is obviously an intensive step as well. Now, what's interesting here is that this step took exactly or roughly the same time as the data step in this concrete example. So it was also around 12 weeks in this very concrete example we have been going through with a customer for a POC. So you see the data phase as well as the development stage are important, but they sometimes take the same time, and it shows the significance of handling the data is a very, very important step. And then finally, the deployment step is where we, in the case of deep learning, do so-called inference. So we use the trained model and apply it to new data, so new pictures for this industrial structure, for instance, and then I can see whether there's corrosion I need to take care of, right? So this is what we do in the inference status step in this concrete example. So again, this is obviously a principal point of view in terms of how do you go through those 4 steps, but I think it's good to know that for the next few things I want to talk about together with you. And that is about the solution, right? How do we actually do a solution? Which hardware and software are we using? And how can we also do this in an HPC AI combined world? So you remember that picture on the left, right? Those 4 phases. How do we actually support this? In principle, and also from our side as Intel. Obviously, you need hardware, right? You need hardware to run HPC, run AI algorithms on. That's very clear. We'll come to that. You need a software stack, equally important to the hardware, and they need to work together very well. And last but certainly not least, what you need to bring solutions together is an ecosystem. Nobody's bringing solutions together on their own, right? So you need to rely on partners, on other companies, on other research to really bring solutions together. And that is a very, very important step I'll talk about in terms of what Intel is doing concretely on that in a few minutes as well. So hardware, software, and the ecosystem. So obviously on the hardware side, you know us at Intel for doing CPUs and platforms. On the software side, we are looking into actually how can we support these platforms, and we have certain ways how to work with the ecosystem. That's what I want to go through with you right now and see where it is actually applied in some further examples. So if we look at the processing side, what becomes clear is that we have a lot of workload diversity. This is not just an HPC phenomenon, it's also an AI phenomenon, right? When we look into traditional modeling and simulation, we have optimizations for scalar architectures. We have also optimizations for vector architectures because we need to do a lot of vector math computations. AI, on the other hand, is also not a single workload, right? On the one hand, you need to manipulate a lot of data, right? This is more traditional things which work very well on scalar architectures. But then you have specific operations on matrix structures and spatial mathematical operations as well, which are supported by subsequent hardware structures. So what you see is basically also that you need to support AI from the device edge to the data center level as well. So if you put all that together, right, in some cases, you can certainly use one architecture for all of these steps. But if you want optimal solutions, you have to go into a heterogeneous architecture as well. Right? And this is what we are seeing out there, that a one-size-fits-all solution is not always the answer, right? Sometimes you really need to go and use hardware heterogeneity to the advantage of getting a solution done in a fast way, in an effective way. So that is what we are seeing out there. Now, The really big question is, okay, when and where do you use certain architectures, right? And there's no general answer to that. What I want to offer to you today is basically what we have been doing and are doing from an Intel perspective to deliver AI and HPC from cloud to device with different architectures for different use cases. If you look at the broad market where you have a mix of lots of workloads, right? A generic CPU architecture can support all of these workloads and do that from device over edge to the cloud and data center view with respective CPU architecture, in our case, core architecture or the Xeon architecture on the cloud side. Now, when you have requirements for specific applications on the AI side, on the HPC side, on the graphics side, or for real time, this is then different, right? If your workload goes up onto those specific things, then you need the heterogeneity of hardware to support it in the best way, in the fastest way. So you can actually look at using discrete GPUs. In our case, we are just working on the so-called XE architecture, which is a discrete GPU architecture, which can support AI and HPC workloads in a way that those highly parallel workloads can be processed in an effective manner. Now, if you have a very specific workloads like deep learning is, in case of deep learning training and deep learning inference, you have a lot of matrix manipulations, and you can do those matrix manipulations at certain data types which are efficient. Then you might want to look into different architectures, right? Like, for instance, our Movidius architecture, right, which can be used in devices like drones and cameras, intelligent cameras, to run inference in there and do picture analysis right on the edge on the device side in a very efficient manner. Also by the side condition that you don't have a lot of electrical power in battery operated environments like a drone, you need to be very efficient there. So this is a specific architecture for usage for that. On the other hand, you can have very high training requirements in the data center, also inference requirements in the data center. Here we have an architecture in development together with a company which we acquired about a year back, Habana Labs, with their Goya and Gaudi architectures, which are in development to address training and inference respectively in a very efficient manner. So this is a few examples, right, of architectures from our side, from cloud to device to support AI and support HPC in a very efficient manner. Now, if you look at at one specific example here from the Xeon side, right, we are heading into the third generation of Intel Xeon Scalable processors, so-called Ice Lake, and we are introducing a number of new technologies here, right? So we're looking into having higher memory bandwidth with 8 DDR4 channels. We have faster I/O with PCI Gen 4. And a number of other things, last but not least, also security innovations, which are very, very important for handling data in the AI space. So this is our upcoming architecture, which will ramp into volume in Q1 of next year. So it's not out there yet, right? But will volume ramp in Q1. 21. Now, if you want to know how efficient that architecture is for certain areas, I have a few performance numbers on the bottom, right? Compared to competitive architectures, we're doing pretty well in early testing, right? We have tested LAMPS, NAMD, and Monte Carlo. So these are key life science and financial services workloads, and we see a very good performance in early testing versus other architectures out there in marketplace. So looking forward for that architecture. Again, this is our generic architecture, and it also has technology built in which supports, for instance, AI in a very specific way with very fast arithmetics on lower resolution data types like int8 for the case of inference, right? Just to name one architecture, which we call DL Boost technology. And this is also built into this architecture. So a number of things we bring together in this architecture, in this generic CPU architectures to help different workloads to cover this case where customers have a lot of workloads. Now, one architecture I wanted to also give a more close look at is our upcoming GPU architecture called XE. And here we actually target with one architecture and 4 micro architecture a very broad market from entry markets, right, into mid-range graphical markets on desktop, into the data center supporting AI and HPC up to the very extreme HPC exascale case. So this architecture has a wide range. And again, as I saw it in the picture before, this architecture is obviously supporting AI and HPC workloads when we have very high requirements to do those things, and also supporting graphics like a TPU is designed for. Now, as we are developing this, and not all of these products are out yet, right? I just wanted to give you a brief look at one thing we just brought out on the server side, the so-called Intel Server GPU, which is based on the XE architecture. And that is not specifically for AI and HPC workloads, but it's more focused on cloud gaming and media. This is just to give you an example that this architecture is out there. It's also out there in the desktop space already for graphics. And we are developing this architecture to also support us in this realm of heterogeneous architectures on the HPC and AI side as well. Stay tuned for that. Now, that was the hardware and a few things I wanted to tell you about it, right? But the software side is very, very important, specifically if we have those different workloads which need diverse hardware architectures. I spoke about that before, scalar, vector, matrix requirements. And they are obviously matched with CPU, GPU, FPGA, and other accelerator architectures. Now, how do we bring this hardware and the actual workloads together in a way that it is very efficient? And we don't need to do the programming every time very separately with separate tools and with a separate software stack, which is obviously costly, right? And we want to avoid that cost, right? So our idea was to say, okay, how can we do that and bring together things as much as possible, right? And this is when we came up with the One API Industry Initiative. So this is an open initiative which centers around a few things like a unified language called DataPel C++, and it is actually targeted to bring these performance requirements with this middle layer level software onto the right architectures without having to use different kind of tools on the software side a lot, right? And it is built on existing HPC programming models like OpenMP, like programming languages like Fortran, and the MPI message passing libraries, just to name a few. So this is both an industry initiative as well as an Intel product built on this industry initiative, right? And it extends into architectures which are actually not just coming from us, but also from other places as well. Now, let's look at the journey we have been through with this. So the industry initiative was announced about a year back, a little bit longer than a year. And we have been working with a lot of players in the market, customers and developers. And we have just released the One API 1.0 specification. And now we have announced a few days ago the Gold One API toolkits, which is our implementation to basically bring the heritage of proven software tools into new architectures and also bring the next generation of our development products based on the principle of One API with the so-called One API toolkits. And what we also offer is the Intel Dev Cloud, where you can actually try this hardware-software combinations, right, built on CPUs, FPGAs, and also discrete GPUs upcoming, with no downloads, no acquisition of hardware, no installation. You can basically try out your workloads and see whether this hardware-software combination, One API, is actually working for you. This is an offer you can take up by going to that link and register. Obviously, it's not meant as a commercial offering in terms of running your whole workloads on that, but it's basically, as the name says, for developers of applications to try out the One API software and hardware stack. So I hope that might be a good offer for you. Here you see a few more details on the various toolkits we are offering going forward. The base toolkit, which has the DataPel C++ language, and then various toolkits which add on to that. And as you can see, there are specific toolkits on the analytics side and the AI side and HPC side, which will offer support for your programming of diverse architectures for your AI and HPC applications. So I just recommend you looking into this in more detail than I can provide insights today. Now, how does that look for AI acceleration in more detail, and what are we doing around that, right? You might have seen that some of these elements I was speaking about were integrated in the One API stack, like OpenVINO, which is a tool which supports developers in deep learning usage for using their trained models very efficiently on different kind of architectures. And we also have another important aspect here. What we are doing is supporting standard frameworks like TensorFlow and PyTorch to run very optimally for deep learning, for data scientists usage. And last but not least, with Model Zoo and Analytics Zoo, we are going up one level and basically offering AI models as examples and ready to use pre-configured models for starting your development on AI applications. Just to give you a little bit of a view of what kind of tools are available from our side to start your AI journey and combine it what you have been doing already potentially with HPC. Okay, so let's look at the last element I have been discussing before. Remember those three pillars: hardware, software, and then ecosystem. And also around the ecosystem is obviously the question on how I bring solutions together with others. Now, if we look into that ecosystem setup, right, we have a large number of ISVs, integrators who are building solutions which can actually help you and us to build AI solutions. And I just wanted to give you this one example of the Intel AI Builder program, where we actually are working together with industry-leading ISVs and integrators basically to accelerate the adoption of AI technologies by making sure that those solutions work very well. And there's also a website where you can look up those solutions. And if you're looking for a particular solution element, like very specialized image recognition for, let's say, retail or various other things, you can actually go to this website and look for partners you can work with to do that. Because as I said before, nobody is building their solution on their own completely. So we need to work together with others to make solutions really work. And there's a few other things where I won't go into detail. We offer obviously our technologies also on the public cloud, as you can see here, and we're helping OEMs to really make sure that the right architectures are out there. Another aspect of that is also Intel Select solutions, where we can actually pre-configure, or you can look up pre-configurations which have been benchmark tested, so you make sure your hardware software combination is actually working well for the problem you are targeting. So just a few things we are doing around solutions. Remember those 3 steps: hardware, software, and ecosystem / solutions. We need to bring all of that together to be successful in AI and HPC combinations. Now let's look at a few use cases before I wrap up my talk here to make sure that we also see whether this, how is this applied with other use cases. I was speaking about the necessity we have upon us with the COVID crisis to really accelerate insights, right? And there's a number of things we have done from our side together with others to bring that forward. You can see a link there where a lot of these examples are featured. Just one thing I wanted to bring to your attention: we have been working with the Berlin Institute of Health in Germany, and their problem is actually working on looking at the virus, right, and understanding how it actually works in the human body. For that, you need to do RNA sequencing. And that one is obviously supported by using high-performance HPC clusters, right? And this is what the solution is about. How can you use HPC clusters, high performance, to really speed up the RNA sequencing in understanding how this virus works, and then obviously supporting how we can actually find cure for that, which is already ongoing since a while. Just a few examples on that one. And another one out of the more research side at the Max Planck Institute, they are looking at brain analysis. And in that case, we were able to help them with the OpenVino tool, which I've been speaking about before, to help them to reduce their memory requirement for image processing. They have very large images, and they are basically 3D images in a way. And that would use a lot of memory, or does use a lot of memory. And you need to find a way to run this efficiently for the inferencing case, where you need to look at new pictures. To actually reduce the memory requirement is a good thing there. And they were able to do that with the OpenVino tool as an example of how tools can be used to basically bring research forward in this case. There's a lot more examples, right, than I can talk about today. You can look up some of them at the HPC Wire channel, which we have built just 1 or 2 weeks ago when SC20 was starting. This is still online, right? And I recommend you to go there and check it out. A number of the things I have mentioned are featured there in more detail. For instance, just to come back to that example, remember that CERN OpenLab example where they're using 3D GANs to speed up the discovery they want to do, replacing some HPC simulations based on Monte Carlo. When you go there, you can learn more details about that. Also, how they have been using our tools successfully as well to speed up the AI part of that solution significantly by using reduced data types like int8 together with the tools, the hardware support we offer in Xeon, as well as the software support in various tools we offer. So check that out, right? There's a lot of good examples there how AI and HPC can work together in general and in specific cases. Good to learn from that, and I hope that inspires you for your own endeavors in building solutions. Now, looking forward, right, we have a number of key trends, right? AI and HPC will require more cycles, right? So we're all looking into exascale computing. You probably have heard that we're working with Argonne and the Department of Energy in the US on the Aurora project, where you will see some of these technologies I was speaking about, which come in the future, like our discrete GPU architecture, in this case called Ponte Vecchio, codename Ponte Vecchio, coming together. But there's also other things going forward, which are interesting developments, like the neuromorphic computing, which is a different approach into using AI, more modeled like the brains are working, or at least how we think the brains are working. And here we have several chips which our Intel Labs facility has developed, right, to basically look at them, look at this area from a research perspective. And also we are working on several places in terms of quantum computing as a promising technology for the future to solve even more problems going forward. So you can see there's a lot of things in movement today, in the near future and in the further future, which are very interesting in the field of AI and HPC together and combined. With that, I would like to thank you for your attention, and I hope I was able to bring a few ideas across to you, which are helpful for your own work going forward. And thanks again for having me here. I always like to support CHPC, having been following this conference for a long while, and I enjoy to be with you today. Thanks a lot.
Thank you, Stefan. A very interesting talk and relevant to the NICIS. As we produce more data, we need AI and HPC so that we can make sense of that data that we're producing. We do have some questions that we need to address before you leave. I will read out the questions and then you can respond.
Sure.
The first question is from Kasim Mitondi. With deep learning, you are always likely to work with data that does not fit in memory. What is your relevant architecture for supporting those work on a single computer, and how does it work?
Yeah, thanks for that question. Obviously, memory is very important, and the whole memory hierarchy is very important for AI. They usually have lots of data like images and other things. So what are we doing there? We do several things, right? If you do AI on a CPU, right, you automatically have a larger address space than in some other architecture. So that already helps. Then we are introducing new memory technology into the memory hierarchy, right? We have persistent memory introduced, right, a while ago, right, which actually enhances the memory architecture in a way that you can store more data in an easier way, in a performant way. So these are some examples, right? Obviously, you also need to make sure that the speed you can transfer memory in and out of your processing architecture is there as well. So many things ongoing there. Obviously, we can't go too much into detail there, but a lot of things we are doing here.
Stefan. So the next question is from Nyameko Lisa. Thank you very much for the interesting presentation. Can you perhaps provide some insight on the prospective solutions and or framework and of implementation of one API across a heterogeneous system? In particular, on a very high level, could you perhaps elaborate on how one API could be deployed to concurrently, simultaneously take advantage of a system, both modern Intel CPU, AVX 512, and flagship NVIDIA GPU, for example? How can the one API and respective ecosystems overcome the need to build applications for specific target hardware architecture? Thank you.
Yeah. That's a great question, right? So one API's goal is obviously to be architecture independent, hardware architecture independent, right? And we achieve that by basically saying, okay, there are certain libraries you need to have for specific architectures, but on the user end, you want to have, first of all, for HPC, a language and a setup which works across architecture. So what we are offering there is DataPel C++, right? And there has been, as this architect, as one API is not just a series of Intel products, right? Which is nice to have, but on the other hand, this is also an industry initiative. Though the intention clearly here is to support architectures in a wider way, right? And there has also been some experiments done. I couldn't bring this example here, but it exists on the pages I have been pointing to, where certain users actually have been porting applications which have been written for other architectures on GPUs, just to say that, onto this one API approach, and they were able to achieve success in porting as well as in performance on these architectures as well, using one API. If you send me your contacts, I can point you to the right place, right? It's featured on one of these HPC wire channels, which I have been talking to before. So there's a couple of examples where people have been able to do that. And what you've been asking for in your question is exactly what we intend with this initiative, right? And obviously we have been driving this initiative from an Intel perspective, but it's an open initiative, open to other architectures, clearly very well as well. I hope that answers the question.
Thank you. Yes, Stefan. Our last question is from Melon Joshua. The question is, hi, Stefan, and thank you for your brilliant presentation. I have a question on processing hardware heterogeneity, workload optimization, and acceleration. Slide 30 on your presentation. Why didn't mention the TPU, which with its tensor configuration has been very efficiently lately for accelerating the training of some deep learning models in AI?
Yeah, if you refer to TPU, obviously tensor operations, they are in several architectures, not just in what people call TPUs today from certain vendors. So you can see them in other architectures as well. And basically the remember that slide when I was talking about matrix architectures, that is subsumed there basically. So architectures which support matrix manipulation in a way can be done differently in hardware, but I couldn't go to all of these architectures, but it's basically matrix architectures. And the implementations of those architectures are obviously different, right? And hence I wasn't going to this particular example.
Thank you. Okay, so there's another question that came in. It's from Onyoti Velmina Nekoto. Very informative presentation, Stefan. Thank you. Kindly advise, what are the major differences between the Xeon architecture and Movidas architecture, particularly on low resolution data and interference tasks? If so, can I use them both when designing a solution? Number two, which model will be best when dealing with real-time tasks for inference on low resolution or noisy data, such as objects in the Kruger or the desert? Regarding use cases, where will be the Intel Trail Guard device for?
Yeah, so a couple of things in one question, really. Let me try to do that step by step. So the architectures are obviously different, right? The Movidius architecture is a very specialized architecture for running deep learning inference, visual deep learning inference, to be very exact, right? So I won't go into the architecture details. The Xeon architecture is very different, right? It's a generic CPU architecture, right, which is specialized for the data center and to run a lot of workloads, right? Now, when it comes to data resolution, right, there is a technology in the Xeon architecture from the second generation onwards, which is called DL Boost, which actually supports very fast manipulation of int8 data, which you can use for a lot of inference cases, right? So you see a speed up there, like I was hinting to, and can give you more data on that as well in a separate session if you desire. On the other hand, what you do obviously with the Movidius architecture is this visual inference, like you hinted to that example, right, of using a Movidius chip in a mobile camera where you have only battery operated, and this needs to run for a long time, right? Like in the African bush, we actually have a nice use case on that. Now, the question is really, can you use certain tools on the software stack to support both architectures, right? Without doing it fundamentally different, right? And this is where a tool like OpenVINO comes in, which can then do quantization and other things to optimize for a specific architecture without the need to do that from an application developer perspective directly, right? So this is actually a good question because it brings out that we can basically train a model, right, to do image recognition for animals in the bush or other things ongoing in the bush, right, which you want to detect. Like humans running around in a place where they better shouldn't, and it's suspicious, but still basically differentiating humans against animals in their place. This is a concrete case which we actually have researched. And then you can basically train that on a Xeon. You can even run it on a Xeon for inference, but you actually want to run parts of the inference on a very mobile device, which runs on battery power. In this case, this was a device built with a Movidius architecture as the central processing unit in there, and it actually shows that we have been able to use optimization technologies, right, to bring it onto this architecture as well. So I hope that answers your question, right, without going into too much detail. But the core of the thing is here really, can you target different architectures, in this case for inference, with a model which has been trained on an even different architecture again? Yes, you can, if you use parts of the one API stack, in this case, the OpenVINO tool.
Thank you, Stefan. So this will be our last question. We've exhausted all our times and you've done well. Thank you so much. I will hand over to the program director.
Yeah, thanks a lot. Again, from my side, it was a pleasure to be with you. Thank you.
Thank you, ladies and gentlemen. That brings us to the end of the keynote 2. We will now break for a lunch break from 1:15, and we will resume at 2 o'clock with the parallel streams, HPC application and HPC technology. Thank you, ladies and gentlemen. We will see you shortly.